her best bet to getting access to a document is to use all of her credentials. It makes it so that it's most likely. However, if you have this non-moneticity, this isn't the case. But there's more practical problems with this. A lot of times when you're asking for an absence of a credential, that's a fairly special case. Most people don't have that credential. And so you can try to reverse it. So in the case of the bad driving record, you could have a credential for a good driving record. But if you did this for all the possible things where you could have a not of something negative, most people would have to get a very large number of credentials, which make the system not usable. But there's another problem. So consider a credential for this person is a millionaire. It's fairly easy to prove to someone you are a millionaire because you can go open all your bank accounts. You can open up all your, get all your credit reports out so they know how much debt you have. And you can show, well, I have a net worth over $1 million. But proving to someone that you're not a millionaire is much more difficult. How do I know that you don't have $1 million stashed away somewhere in your basement somewhere? And it's much harder to certify something like you are not a millionaire than it is something to have you are a millionaire. So having the absence of a credential doesn't work in many cases. Also, even if you have a trusted third party, Alice can carry out an online probing attack. She can ask Bob for the same message many times. And each time she can try a different set of her credentials and therefore glean information about Bob's policy. This is unavoidable in our model. However, it's worth noting that Bob really can't do this because he doesn't know if Alice gets access or not. This being said, there are cases where Bob can infer information about Alice getting access or not. Suppose that a message M1 has a hyperlink to message M2. And shortly after asking for M1, Alice asks for M2. Bob doesn't know that Alice got access to M1, but he knows with some degree of certainty that she did. So Bob might be able to do some form of probing with these types of techniques. We don't really consider this a big problem, though, because Bob knows when Alice is doing this to a degree. Because if Alice is asked many times for the same message, Bob knows this. So he can just implement a simple policy. He can only ask the message person. Yes?
You said if Alice was granted access or rejected access, she wouldn't know the reasons why, which
right.
Wouldn't that, in a realistic situation, be more of a hindrance than a good thing? I mean,
it depends on what you're doing, right? I mean, yes, you could have... If someone had a bad policy, you have to be of a certain ethnicity to get access to this. That would obviously be something that's bad. However, in like a government situation where you have top secret clearances,
right,
that is a very desirable thing that you don't know why you didn't get access.
Well, wouldn't you I mean, if she's working for, say, the CIA and she has the wrong security clearance, I mean, she doesn't know if it's because of her security clearance, department, gender, or whatever, and I mean,
well, it does depend on your situation, right? I mean, yes, you could, if you're an internal CIA server, then, it's probably not the case that they're going to deny something because of gender, right? It's more that they're going to deny something because of security clearance. And a lot of times, like the different departments in a top secret project have confidential names. So they can't just go around telling everybody the access policies.
Right.
Also, if you take an example like the TSA, they have certain criterion they look at, but they don't want people to know those criterion, right? Because if they told everybody those criterion, well, it makes it that much easier to game the system, gain access to the system. So there are cases where you don't want to reveal that information. There's a lot of work in trust negotiation that's fairly similar. A lot of times, some of the work tries to minimize the disclosure of credentials or policies. However, they don't quite achieve what we've achieved before. They usually have something to the degree of, if you gain access, you found out why you gain access, which is something that we're trying to prevent. This being said, it's not that this work completely, it's a superset. The work that I'm presenting is a superset of this work that is better in every way, because while ours has a higher degree of privacy than a lot of this, it also requires more computation and is more inefficient. So it's kind of a proof of concept that you can do all of these things rather than an efficient system that's useful. There's also some related work in the area of secure multi-party computation. Secure function evaluation, particularly, it allows, if Alice and Bob have private inputs A and B, it allows them to compute some function that's an aggregate function on those inputs without revealing anything other than the input and output alone, which clearly has a relation to what we're doing because we want to be able to evaluate a policy without revealing anything other than what can be inferred from the input and output alone. The difficulty there is that the function in secure function evaluation is usually a public function that everybody knows. And so it doesn't quite work because in our case the function's hidden. One person knows the function, the other person has the inputs. There has been some work in a secure private function evaluation, but this was really more about special cases. And the model was that one person has a large data set and another person has a particular function. And the person with the function likes to evaluate the function on a subset of the data set. And so it's not quite the same model that worked, but it is related. Also, a special case, a particular secure protocol that has an implication is a secure private intersection. This being said, there are some differences between the related work and this work. First thing is that in typical secure function evaluation, one of the things that's always said is that, well, Alice can lie about her input, Bob can lie about his input, which makes it not immediately usable in this case because if Alice's input is her attributes, she can just lie about her attributes, which makes Bob have no trust in the system. But instead of this being the case, it's really a third-party verification of the attributes. This is complicated by the fact that this verification is done by a certificate authority who does not need to be online when this is happening. If the certificate authority was online when this is happening, you could expand to a three-party protocol or something to this degree. But if you had the certificate authority being an active part of this, it would become a bottleneck in the system. What makes this different from a lot of the work in trust negotiation and hidden credentials is that the goal is to reveal nothing. You're not supposed to reveal Alice's credentials. You're not supposed to reveal the policy. And you're not even supposed to reveal the outcome to Bob. So there's a high degree of privacy requirements. So at this point, we've been over kind of what the goal of the system is. There's a few building blocks that are used by the system. One is scrambled circuit evaluation. And this was introduced by Yao in 1986. And essentially, it says if you have a two-array circuit for evaluating some function f, and it has m gates and m input wires, then you can evaluate this with order m communication and order m evaluations of some pseudo-random function. An example of a pseudo-random function would be something like AES, which is fairly efficient. Also has order n 1 out of 2 oblivious transfers. Oblivious transfer tends to be a fairly expensive operation. Usually requires some form of public key crypto, so something on the order of a modular exponentiation. But it also only requires a constant number of rounds. In order to explain things later, there's the way this protocol basically works is there's a circuit generator who creates some scrambled circuit of some form. He sends this over to some evaluator, and the evaluator, while each doesn't know what he's evaluating, what he's evaluating, but he does know at the end of the day what the circuit computed, but he doesn't know what the intermediate values are. Also, there's a particular secure protocol, set intersection, that was introduced in 2004. And in this, we use a kind of a special case of this. Is that this is a one instance of being able to do this. And basically, Alice has some set of values, and Bob has some value xb. And if xb is in the set of values, I flipped the XA should be XB and SB should be SA in the later part of the slide. And if XB is an SA, then Alice will learn the value RB. Otherwise, she learns some random value that's indistinguishable from RB. So at the end of the protocol, Alice doesn't know if her values, if Bob's value is in her set, but she has one particular value that is something if it is in the set. And this requires communication proportional to the size of the set and a similar number of modular exponentiations, yes.
Does that use a trusted third party?
No. It's two-party protocol, can be secure in a malicious model, and all these things. One more building block is identity-based encryption. This was proposed by Shamir in 1984, and basically, in this case, it was a request. We'd like a crypto system with the following properties. And there were many systems that attempted to achieve this that either fell short or were subsequently broken. There's been a recent scheme in 2001 that actually achieves this in many ways. But the goal of the identity-based encryption system was to implement a public key